Okay, when we finished off on Thursday afternoon, we had determined that the first solution to the first order differential equation was a decaying exponential. Um, Notice the negative sign. That may have been a mistake I made, not including it correctly, but it's there now. So that's the correct form. And then we come over to our second differential equation, which is second order. And this happens to be of the Sturm-Liouville form. And so we're not going to solve this equation. We're just going to write down the solution because we know that it's a sine and cosine solution. And the reason is that the sign up here is positive. Otherwise, it would be cinches and coches, right? All right, so there's the solution to our two differential equations. And I promised y'all that what we were going to do was apply our boundary conditions. So as you remember, our first boundary condition is that at a position c equal to 0, x is equal to 0. Simple. We love those zeros, don't we? All right, so if we plug that in, we get that x of 0 equals a sine of 0. Obviously, that vanishes. Plus b cosine of 0. That's 1. And so this gives us, contrary to what we have written here, that b equals to 0. So we've solved for our first constant of integration. The constant of integration multiplying the cosine term is 0. And that means that our new expression for x is only a function of sine. Awesome. So now we can apply our second boundary condition, which is at a position c equal to 1. And again, that's a homogeneous boundary condition, meaning that we've got a 0 there. Makes it easy to solve. So x of 1 is 0, and that is a sine of lambda equal to 0, because of course we've set c equal to 1. So this is a little bit trickier because we went into this thinking we were going to solve for a. We do not want a to be 0. Absolutely not. That will remove our sign dependence. So we're going to get sine of lambda equal to 0. And so it turns out we're actually going to be able to use this boundary condition to solve for our eigenvalues, but not for our constant of integration. So, it's not brilliant, but it's good enough, right? So sine of lambda equals 0 when lambda is any multiple of pi. But we're going to exclude pi equal to 0 because that will collapse our solution into a linear dependence. Mathematically, perfectly fine, but physically not acceptable. Our dependence on time is absolutely not linear, so we're only going to take those solutions which give us a more complex result. And so that's n equal to 1, 2, 3, so on and so forth, all the way to infinity. And once again, because we have an infinite number of eigenvalues, we know that we're going to have a series solution. So we can plug in our lambda value for our solution at this point. We still haven't solved for our constant of integration, but at least we've made a little bit of progress with lambda, so we know that that's n pi. Again, we have our c dependence. And these are all eigenfunctions of our equation up here, which is the solution just focusing on the x terms. So we've solved this, we've applied our boundary conditions, and we're pretty well on the way to a full particular solution. So in order to use our last boundary condition, we're going to recombine our separated variables. So you recall that we made up this concept that theta was going to be a function only of x of xi and y of tau, and being unable to disprove it, we're going to continue to believe that's true. And that's exactly the kind of crap that mathematicians do. So we'll plug in our value for x. That's again a sine n pi xi. We've solved for y, but we haven't solved for the constant of integration. So we've got c1 exponent negative lambda tau. I believe that's a lambda squared. So we've got our full eigenfunction solution. We can see it's pretty plain that a and c1 are not independent, so we can just write them as a single constant of integration. And we know that because we have an infinite number of values for lambda, that we're going to have an infinite series solution. So we can just go ahead and write that summation over infinity. So we'll call our constant of integration be index n is any value from 1 to infinity. And then we've got our sign dependence on xi, and we've got an exponential dependence on tau. And I'll write this as n pi. We can substitute in for our value of lambda. It's always nice to obey bracket rules appropriately. Square brackets on the outside, round brackets on the inside. And here's our solution. This is absolutely a solution to the differential equation system. However, until we're able to solve for this one remaining constant of integration, Bn, it's not a particular solution, and so it's not really going to help us in the physical world. So to get to our final solution, we're going to apply that last boundary condition, which is that at all positions xi and any time 0, the temperature was T naught, which non-dimensionally is 1. So plugging that in, that means we basically insert 0 everywhere we see tau in our equation. So we'll do that. And you can see where this is leading up to. Anytime we have a series with a sign in it, we're going to do something with a Fourier sine solution. So of course, the exponent of 0 pulls this term out. That's just unity. And we're left with a simple dependence on the sine term. Okay, so very quickly, we're going to evoke the Fourier sine law. You've seen this last week. You know what a Dirac delta function is. No mysteries here. We just want to make this expression look as much like a Dirac delta as possible. So we're going to multiply both sides by the sine of index m pi xi, because we need a different index. And that will get us significantly towards looking like something we can solve. So we go ahead and do that. The left-hand side, we integrate from 0 to 1. The solution is a negative cosine. I always have to look this up. Don't feel bad if you forget what the integral of sine is or the derivative of cosine. It's ridiculous. You can just draw a picture or look it up on Wikipedia. We're integrating on the bound 0 to 1. And we'll go ahead and solve this left-hand side completely. Why not? So the cosine of m pi when xi equals 1 is negative, minus a positive, minus a negative, cosine of 0 is just 1, all over m pi. And so our final expression for this left-hand side is just 1 minus the cosine of m pi over m pi. And we can be quite clever here. We could substitute for this cosine of m pi, recognizing the fact that m is only going to be an integer from 1 to infinity, and it's going to be switching signs. So we could, if we wanted to, we could write that as a negative 1 to the m power, and it's kind of a slick way of slightly simplifying the expression, but not essential. Whatever floats your boat, it's all correct. Now we tackle the more challenging looking side of the equation, which turns out to be actually pretty easy. This is our right-hand side. We have something confusing with the summation, and we have that constant of integration. But essentially, we've got these two sine terms. One is indexed to n, and one is indexed to m. And the only point in the mathematical plane where this is going to have a non-zero value is when n equals to m. And at that point in time, the integral is going to have a value of 1/2. We've still got this constant of integration floating outside the integral, but we have this beautiful relationship whereby the sum multiplied by the constant is the same as the constant multiplied by each term in the sum. So we don't have to worry too much about that. We're just going to say that this side is going to equal bn times this integral, which has a value of 1/2. So bn over 2. And that's equal to the left-hand side of our equation, which we see if we come down here. Bm is therefore going to equal 2 times our cosine term and that was the whole palaver. That was all we were trying to get at, was what is the value of the constant of integration. So now that we know that, we can plug that back into the solution to our differential equation, and we have the complete, the glorious and grand, full particular solution. And this means that we can actually do some maths. So we're just plugging in that value of bn here. We're keeping our sign dependence on xi and our exponential decay dependence on tau. It does not matter at this point whether we use the index m or n, as long as it's always used the same throughout. And we have our full particular solution. So thanks for working with me, and I'll see you next Tuesday. Take care.